Hi everybody. It's the second lecture in a series on fluid mechanics. In this case, we are going to look at a specific aspect of fluid mechanics called buoyancy. Most people think of buoyancy as a floating force. When you immerse or put a solid into a liquid, this is what sort of makes it float. However, buoyancy exists even when something is sinking. So whenever a solid is put into a fluid, there is some sort of buoyant force acting on it, whether or not it floats or sinks. Also, the buoyant force does not depend on the weight of the object or where in the fluid it is actually located. So the buoyant force of an object as it sinks deeper and deeper into water or any fluid actually remains the same. It has nothing to do, again, with the weight of the object. It has more to do with the fluid itself. So what is the difference between a weight force and a buoyant force? Any object which has a certain mass always has, due to gravity, a weight force acting on it. Now typically in the past we have said weight is simply the product of mass and gravity, and that works. But having talked about density, of course an object itself has to have a certain density, which I'm calling rho O for density of the object. We learned in our lecture on density that density is the ratio of mass to volume, which means mass is the same as density times volume. So another way we can describe the weight of an object is by replacing mass with density and volume. So the weight of an object is the density of that object times the volume of that object times gravity. Interestingly enough, the buoyant force, it looks very similar to the idea of a weight force. To calculate a buoyant force, which is usually the symbol B, it is density times volume times gravity. But there are some definite differences that exist here. A fluid itself is going to have its own density, which I'm doing rho F to say the density of a fluid. When an object is placed inside a fluid, that weight, of course, still exists. But now the fluid itself is going to exert its own upward force, and buoyant force is an upward force. And that buoyant force is based on the density of the fluid and what I'm going to call the volume displaced. In other words, the amount of fluid volume that is actually displaced. Now, if something is entirely inside the fluid, that means the volume of the object and the volume displaced are the same thing. And that can be really convenient in many cases. However, if the object is floating, that's not going to be true. So what we're going to have to do is sort of look at a couple of examples of both. So for example, let's say I've got a 10 kilogram brick here. I can put it on a scale and it has a weight of almost 100 newtons here. And that's always going to be its weight. However, interesting enough, when I put it inside a fluid here, suddenly this scale says it's about 50 newtons. So that means there must be about 50 newtons of buoyant force that's acting on it. And you can see a lot of that has to do with the fact that it has displaced 5 liters of water. And that would give a buoyant force by the water of about 50 newtons. However, a wood block that say is about 20 newtons, if I put it in here, well, this is interesting, it's floating. Now, in order for it to float, think about how the idea of equilibrium has to work. In order for a 20 Newton block to float, that better mean there's 20 newtons of force acting upwards to support it. So that means the buoyant force here has to be an equal 20 newtons. Now again, you'll notice here, it displaces about 2 liters of water, which is the equivalent of about 20 newtons worth of water force. So that's another aspect of the buoyant force. Because the weight and buoyant forces are so similar in terms of equation, buoyant force is also always going to equal the weight of the displaced fluid. Okay, so however much volume of fluid is displaced, whatever that would weigh, that would actually equal the buoyant force. So let's look at the difference between something that is completely submerged in a fluid and something that is floating. Okay, so first we'll look at something that's going to be submerged into a fluid. So here I have an object of unknown material that I've hung from a spring scale, and that scale is showing a reading of 30 newtons. It's then submerged in water. Now the density of fresh water is about 1,000 kilograms per cubic meter. Once it's in there, suddenly that spring scale is reading 20 newtons. So we want to look at a couple of things like the mass of the object, its volume, and its density. We want to consider both situations here. So in the first situation, where the mass is simply hanging by the spring scale, the forces that would be acting on this, of course, would be the weight, mg acting down, and then there would be a tension force from the spring scale acting up. What the spring scale is showing is the tension it is exerting on that particular mass here. So in this case, that would be 30 newtons. Now, of course, looking at that, if I were to sum my forces here, well, I have tension minus mg. Well, it's in equilibrium, so that has to equal 0. And that means that the mass of this thing is about 3 kilograms. When I look at the mass when it's inserted in the fluid, if I look at the forces that are acting on it now, well, the weight is still there, mg, and the tension is still there. But now that it's inside a fluid, I have to consider the fact that there is a buoyant force also acting on this. Now, again, the spring scale is going to show tension. So in this case, the tension is my 20 newtons. mg can't change. The weight can't change. That's still 30 newtons, what it was before. So now if I sum my forces here, well, I have the buoyant force plus the tension minus the weight equals 0. Again, everything is in equilibrium here. Solving for the buoyant force, means there is 10 newtons of buoyant force acting on that. Okay, so what can that help me with? Well, there's a couple things now this can help me with. Knowing the buoyant force would allow me to figure out what the volume of the object is, because it was fully immersed inside there. Since the buoyant force is density of the fluid, volume displaced times g, I know I have 10 newtons of buoyant force. 1,000 is the density of the fluid. The volume displaced is the entire volume of the object. And I have gravity. This gives me a volume displaced of 1 times 10 to the minus 3 cubic meters. Okay, relatively small object. Now, how is that going to help me with finding what the density of the object is? Coming back here to the idea that the weight of the object, which is mg, is also rho vg. In this case, because everything was fully submerged, the volume of the object and the volume displaced by the water are the same number. So now knowing the weight, 30, and the volume, 1 times 10 to the minus 3, gives me a density of 3,000 kilograms per cubic meter. Now that number makes a lot of sense because it was able to sink fully in the water. It didn't float. For something to sink in water, its density must be greater than the density of the water. So that's an example of when something is fully submerged. And the nice thing when you're fully submerged is always the part that the volume of the object itself and the volume displaced will always be the same number. That can be very useful. But what if you're floating out? Now here's an example of something floating. Have a block of wood with a density of 800 kilograms per cubic meter floating in water. And again, it should float because it has a density less than that of water. And I want to know how much of it is actually underneath the water. So again, let's look at a free body diagram. Since it's floating here, of course, it's going to have its weight and it has to have a buoyant force. And those would be the only forces that would be acting here. And again, they would be acting in equilibrium. So in terms of summing forces, buoyant force minus weight would be 0 because it's in equilibrium. Or the buoyant force and the weight have to be equal to each other. And again, that makes sense. It's an equilibrium situation. If I do some substituting here, buoyant force is the density of the fluid times the volume displaced times gravity. Instead of mg, I want to use the other weight equation, which is the density of the object times its volume times gravity. Now right away you can see I can knock gravity out of there, which can be really helpful. But how is this going to find me how much is below the surface? Well, on the buoyancy side, we have the density of the fluid. Well, the volume is going to be the length times the width times that x, the amount that is under the water, because buoyancy is based on the volume displaced, not necessarily the volume of the object. On the other side, we have the volume of the object, and its entire volume is the same length, the same width, but a different height, because we're talking about the full height there. So again, a little bit of quick canceling, and this can be nice, is you can knock some other things out of here. And so now what you end up with is that x, what you're looking for, is the ratio of densities times the original height. So the amount below the water is going to be the density of the object over the density of the fluid times the original height of the object, which was 30 centimeters or 0.3 meters. And that means 0.24 meters or 24 centimeters of that object is now what is below the water line, which means 6 centimeters would have to be above the water line, so you could kind of figure out either one. I want to show one more complicated problem dealing with the idea of buoyancy, and this is an interesting one. This is inflating a balloon with helium, and with just enough helium where it would float in equilibrium. This has sort of an extra little step to it you might not think of. First of all, you have to consider what we're dealing with here. The balloon itself has mass, 20 grams. I can't ignore that. That's going to be an important part. But when I fill it with helium, the helium is also going to have some sort of mass. But I won't know until I fill it up. Okay, so I can't ignore the fact that that's going to have its own mass, and that contributes to the overall weight of the balloon. So that when you consider the free body diagram here of the balloon, you have to consider the fact that you have the weight of the balloon, but you also have the weight of the helium inside the balloon, and then there's going to be a buoyant force created by the surrounding air. Something we don't always think about, air having a buoyant force, but it does. Summing our forces here, we have the buoyant force up, the weight of the balloon down, and the weight of the helium down. Now, again, because we're saying it's floating at rest, everything here is in equilibrium. The question, though, is what volume do I need to inflate this to in order to make this actually work? Now, this is where it becomes a little trickier. But we're fortunate in the fact that the entire balloon, once it's inflated, is completely surrounded by air, which means that the volume displaced and the volume of the object will be the same, and that's convenient. Now if we look at this equation, if we substitute for buoyancy, which was density of the fluid, volume displaced, gravity, we have the weight of the balloon. Now, since I don't know the mass of helium, I have to replace mass with its density and volume, which is again going to be the same as the volume of the object here. That equals 0. Quick step, let's get rid of all our gravities because they will simply drop out. Now what I want to do, a little algebra here, is I want to put these two volume things on one side with the mass of the balloon on the other side. That allows me to factor out the volume. And so the volume is simply the mass of the balloon before it was inflated over the difference in the densities. So we had a 20-gram balloon. Density of air was 1.29. The density of helium, 0.179, which gives a volume of 0.018 cubic meters. Again, it should be a small number. It's a small balloon. So that's how you can do a slightly more complicated buoyancy example. So that's the basic idea of doing buoyancy, where an object can either be fully immersed inside the fluid or floating on the surface of the fluid. See you next time.